So I welcome you all for today's EMF session. Um, in the last class, I have discussed electric field due to line charge and related problems, right? So far we have completed electric field due to point charge and electric field due to line charge, right? So today we are going to discuss about electric field due to surface charge. In my last class, I have given the introductory part of electric field due to the surface charge, right? So as you can see on the figure on the screen, in the figure I have considered an infinite sheet charge, right? I have considered an infinite sheet charge on YZ plane, right? On YZ plane, I have considered this. On YZ plane, an infinite sheet charge I have considered, right? And I'm trying to determine electric field at a point P on x-axis, right? At a point P on x-axis, right? So at a point P on x-axis means x comma 0 comma 0, right? Is the point P, and this point is where the differential width strip is considered is 0 y dash 0, right? So to determine electric field at a point P, the infinite sheet charge is divided into differential width strips, right? Number of differential width strips like this. So this is one such differential width strip, right? So whose width is divided as, right? Whose width is divided as. That's because the width strip is considered at a point 0 y dash 0, right? That means at a distance y dash, right? At a distance y dash, right? The procedure is same, right? So here to determine electric field due to surface charge, we will consider electric field due to line charge, right? Yesterday I have discussed this. So electric field due to line charge is this rho L by 2 pi epsilon naught rho a rho bar, right? So why I am considering electric field due to line charge? Because surface is found by connecting number of lines, right? Surface is found by connecting number of lines. So therefore, electric field due to surface charge is determined from the line charge, right? Is determined from the line charge, right? And rho s is the surface charge density. So therefore, rho L and rho s can be related like this. Rho s is equal to rho s rho s into divide as, right? Rho L is equal to rho s into divide as. You can verify rho L coulomb per meter and rho s coulomb per meter square into divide as is the width of the strip, right? So is meters. So therefore this is equal to coulomb per meter, right? So therefore this equation is satisfied, right? So therefore we can write rho L is equal to rho s divide as, right? So therefore we are determining electric field at a point P with respect to differential width strip. Once we know electric field due to differential width strip, we can determine electric field due to surface, right? Because integrating, if you integrate, you will get electric field due to the entire surface, right? So that is what we are doing, right? So therefore the procedure is same, joining the point P to the differential width strip, right? So this one, right? Joining point P to differential width strips, and this makes, let us say this makes an angle theta, right? It makes an angle theta, right? And rho, here rho we have, right? Here rho. So what is rho? It is the normal distance normal distance from point P, right? Normal distance from point P um, to the axis on which charge distribution is considered, right? So rho is the normal distance. Earlier also we have seen line charge. So it is the normal distance from point P to Z axis. Why to Z axis? Because line charge is considered on Z axis. So therefore, from point P to Z axis is the normal distance. And here, whereas here, it is the normal distance from point P to YZ plane, right? From point P to YZ plane, right? So therefore, we can indicate like this. This is point P, and the surface charge is considered on YZ plane. So therefore, normal for the surface on YZ plane, what is normal? X-axis is nothing but normal. X-axis is normal to the surface considered, whereas Y-axis and Z-axis are parallel, right? They are parallel. In other words, they are on the surface considered. Y-axis and Z-axis are on the surface, whereas X-axis is perpendicular to the surface, right? So therefore, this distance is nothing but from point P to the surface considered is rho, right? So this is rho. So this is the normal distance, right? And we have joined a line from point P, right? From point P to the width strip, and this distance, right? This distance is nothing but r, right? This distance is nothing but r distance from point P onto the width strip, right? From point P to the width strip is r, right? So therefore, from figure we can write like this, right? From figure we can write like this: rho is equal to r cos theta, right? Rho is equal to r cos theta, right? Because this is rho, and this is r, makes an angle theta, right? Makes an angle theta. So therefore, rho is equal to r cos theta, right? Rho is equal to r cos theta, right? And for smaller values of theta, cos theta can be approximated as 1, right? For smaller values of theta, cos theta can be approximated as 1. So therefore, rho is equal to r, right? Rho is equal to r, right? And where r is the distance between what? X00 and 0 y dash 0, right? R is the distance between x00 and 0 y dash 0, right? So that is how we can determine rho, right? And the electric field due to differential width strip is differential electric field, right? The electric field due to differential width strip is differential electric field, right? So therefore, we can write electric field, differential electric field. We can write this as dE bar is equal to rho s dy dash excuse me, 2 pi epsilon naught rho aero bar, right? And let us say this is equation 1, right? So we are determining electric field due to differential width strip. So therefore, it is differential electric field. So therefore, dE bar. So dE bar is equal to rho L. What is rho L? Rho L we know. right? So royal is this royal. You can replace royal with rho s dy dash, right? So this is equation 1, right? And now rho, as we know that rho is the normal distance, and rho is nothing but r, right? So just a minute. So rho is equal to r, right? And where r is the distance between what, x comma 0 comma 0 and 0 y dash 0, right? So r is the distance between that, right? So therefore vector distance, let us determine the vector distance, right? So vector distance rho bar, right? So rho bar is equal to x minus 0 ax bar plus 0 minus y dash ay bar plus 0 minus 0 az bar, right? So therefore we will get x ax bar minus y dash ay bar, right? So this is the vector distance, right? And in cylindrical coordinates, right? In cylindrical coordinates, this will become rho arrow bar minus y dash a ay bar, right? So sorry, no need of not this one. Let it be like this, right? And let us say this is equation 2, right? And um, rho is equal to, rho is the scalar distance mod rho bar, and this is equal to root over x square plus y dash square, right? And now arrow bar arrow bar is equal to rho bar by mod rho bar, and this is equal to rho bar x ax bar minus y dash ay bar divided by square root of x square plus y dash square, right? So this is arrow bar, right? And let us say this is equation 3, and this is equation 4, right? So therefore substituting equation 3 and 4 in equation 1, we will get, right? So what we will get, substituting equation 3 and 4 in equation 1, right? So we have dE bar is equal to rho s dy dash divided by 2 pi epsilon naught rho. So what is rho? Root over x square plus y dash square is rho, and arrow bar, right? Arrow bar is x ax bar minus y dash ay bar, right? Divided by square root of x square plus y dash square, right? So this you'll get, right? After substituting equation 3 and 4, right? In equation 1, we will get this, right? And now As we know that, as we have discussed earlier, the electric field is normal to the charge which we have considered, right? So for example, point charge, right? So point charge, the electric field is away, right? Electric field moves away from the point charge. So this is point charge Q. So electric field directs away from the point charge, right? Directs away from the point charge. Similarly, if you consider a line charge, so this is the line charge, and what is the direction of electric field? Is away. Away in the sense what? Normal, right? Normal to the line. Everywhere it is normal to the line, right? So therefore electric field exists normal to the line charge. Similarly, here we have considered a surface, right? Here we have considered a surface. Then the electric field, the direction of electric field due to surface charge is also normal, right? Is also normal to the surface, either it may be this side or the other side, right? So this is the normal, right? Electric field is normal to the surface, right? So that means what? If surface is on xy plane, yz plane, right? So surface is on yz plane, then the electric field will be in x direction, right? Because x-axis is normal, right? X-axis is normal when the surface is considered on yz plane, right? So therefore electric field directs in x direction, and electric field can be neglected in all the other directions, right? Electric field can be neglected in all the other directions, right? So therefore here in this expression, the term electric field, in y direction, this can be neglected, right? Right. So since here I will write, since electric field is normal to the surface, right? Electric field is normal to the surface, then ay can be neglected, right? Electric field in ay direction can be neglected, right? So neglecting electric field in that direction, right? So we have the simplified equation like this, is equal to rho s by 2 pi epsilon naught x square plus y dash square, right? Into x ax bar, right? So this into this, you'll get whole square and x square plus y dash square you will get, right? So this is the simplified equation. And now this is the electric field due to differential width strip, right? So if you want the electric field with respect to the entire surface, right? With respect to the entire surface, then integrate, right? Integrate it, right? So therefore E bar is equal to, right? E bar is equal to integral, right? Integral, and one more thing, rho s is constant, 2 pi epsilon naught is also constant, that can be taken outside. So therefore integral x by x square plus y dash square, um, sorry, here I have forgotten, dy dash is there, right? Dy dash, so dy dash ax bar, right? So integrating, and what are the limits of integration? Minus infinite to infinite, right? Minus infinite to infinite, right? Because I have considered infinite surface charge, right? So therefore integrating, right? Integrating this, rho s by 2 pi epsilon naught rho. So integrating this x by x square plus y dash square, you will get tan inverse y dash by x, right, over the limits minus infinite to infinite ax bar, right? So this you will get, right? So let me confirm whether it is this, right, right, and integrating, right? So integrating and substitute the limits, right? So integrating and substitute the limits, and if you simplify this, right, if you simplify this, you will get rho is by 2 epsilon ax bar, you will get, right? So this you will get as the final equation, right, right? So simplifying, integrating, and substitute the limits, right, and you will get, right? If you do so, right, if you substitute the limits here, you will get pi, right? You will get and pi will get cancelled here, and you will get this equation, rho s by 2 epsilon, right, rho s by 2 epsilon naught ax bar, you will get, right? So this is the final expression for electric field due to a surface charge, right? Ax bar. So what is meant by Ax bar? Ax bar is the direction of electric field, right? Ax bar is the direction of electric field, right? And is away, right? Away from the away from the surface charge, right? Away from the surface charge, right? If you go back to the figure, right? So this is the figure, and now ax bar. So what is ax bar? Ax bar is this, in this direction, right? Ax bar, right? So this is ax bar. So therefore, electric field is towards the point, right? Here, the point is considered on x-axis, right? The point is considered on x-axis, right? So therefore, it is ax bar, right? So on the other hand, right, here I will um, give you some cases here, right? So let us say x-axis, y-axis, and z-axis, right? This is negative x-axis, right? So here in this case, we have considered, right? We have considered just a minute. We have considered a surface on yz plane, right? We have considered a surface on yz plane, and electric field is considered at a point on x-axis, right? At a point on x-axis, and from the discussion, from the derivation, we have seen that the electric field directs towards the point, right? Ax bar, right? Towards the point Ax bar, right? Now, contrarily, if the point is considered on negative x-axis, right? If the point is considered on negative x-axis, then what is the direction of electric field? The direction of electric field is again here towards the point, right? Towards the point. Here is the point we have considered, and the direction of electric field, right? Electric field is towards the point. Towards the point in the sense what? Negative x-axis, right? So therefore, the direction of electric field is minus ax bar, right? Is minus ax bar. Therefore, electric field is given by E bar is equal to rho s by 2 pi epsilon naught minus ax bar, right? Minus ax bar, right? So therefore, if you consider a point on this side, the front side of the surface, right, then it is ax bar. If you consider point on the back side of the surface, then it is minus ax bar, right? So similarly, right, similarly, if you have considered, let us say, x, y, and z. If you consider, right, so if you consider a surface, this is minus y, this is minus. Now if you consider a surface on xz plane, right, xz plane like this, right? If you consider a surface on xz plane like this, so this is the surface on xz plane, right? Xz plane. What is the direction of electric field? The direction of electric field is y, right? The direction of electric field is y, because y-axis is normal to xz, right? Y-axis is normal to xz. So therefore, if electric field is considered at a point here, right? If electric field is considered at a point here, then the electric field directs towards the point, right? Directs towards the point. So in this direction, in the sense what? In this direction, in the sense positive y-axis, right? Positive y-axis. So therefore, electric field is equal to rho s by 2 epsilon naught ay bar, right? So if the point is considered on the other side, back side of the surface at this point, then the electric field directs towards this point like this, right? Electric field directs towards this point, like, towards this point in the sense what? Minus ay bar, right? Minus ay bar. So therefore, E bar is equal to rho s
right? Right. So therefore, if you consider um, the surface on xy plane, right, or xz plane, um, the direction of electric field is ay and minus a. If you consider on yz plane, the direction of electric field is ax and minus ax. If you consider surface on xy plane, the direction of electric field is minus az and az bar. Right? So therefore, to avoid this confusion, right? So we can write the expression electric field as like this: E bar is equal to rho s by 2 epsilon naught a n bar, right? A n bar, right? A n bar, where a n bar is the normal unit vector, right? A n bar is the normal unit vector, right? So that means away from the surface, right? Normal to the surface, right? So a n bar may be, it may be ax bar or minus ax bar, it may be ay bar or minus ay bar, it may be az bar or minus az bar, right? So this is the final expression for electric field due to a surface charge, right? So far we have discussed three, right? So let me summarize those. Electric field due to a point charge, E bar is equal to Q by 4 pi epsilon r square AR bar, right? And this is also called as electric field, electric field due to a line charge. E bar is equal to rho L by 2 pi epsilon naught rho A rho bar. And similarly, electric field due to a surface charge, E bar is equal to rho s by 2 epsilon naught a n bar, right? So these are the three important equations which we have discussed so far, right? And apart from this, Coulomb's law also, right? Force, F bar is equal to Q1 Q2 by 4 pi epsilon naught r square a r bar. So this is nothing but Coulomb's law, right? So these are the four important equations which we have discussed so far, right? And we have done related problems with respect to point charge, line charge, and let us try to do some related problems with respect to surface charge now. Right. So related problems. Let us try to do some related problems, right? So that you will understand even more. Well, plane x equal to 3 carries a charge of 10 nanocoulomb per meter square. Calculate E bar at 1, 1, minus 1 due to the surface charge distribution, right? Due to the surface charge distribution, right? So plane x equal to 3 carries, right? Plane x equal to 3 carries. So x equal to 3 is a plane, right? So earlier for a line charge, right? So what is line charge? How it is indicated or how it is located? X equal to 2, y is equal to 5. In other words, x equal to 1, z is equal to 3, like that, right? Like that with two coordinates, right? With the two coordinates, line is represented, right? But whereas a surface, right? A surface is indicated with the single coordinate x equal to 3, right? X equal to 3, right? So that means what? Let me draw here. This is x and this is y. This is z. So a plane in the sense surface, right? A plane x equal to 3. X equal to 3 in the sense plane is located at x equal to 3, right? Plane is located at x equal to 3, right? So x equal to 3 in the sense the plane is perpendicular to x, right? A plane is located at x equal to constant means plane is perpendicular to x-axis, right? A plane is located at x equal to constant means plane is perpendicular to x-axis. On the other hand, if plane is located at y is equal to constant, that means what? Plane is perpendicular to y-axis. And if plane is located at z is equal to constant in the sense, the plane is perpendicular to z-axis, right? So therefore, we can draw like this. Right, so this is the plane, right? So this is the plane at x equal to 3, right? So this is x equal to 3 plane, right? So which is perpendicular to x and is on yz plane, right? At a constant, at x equal to constant, on yz plane at x equal to constant, right? Now we have to consider, we have to determine electric field at a point, 1 1 minus 1, right? 1 1 minus 1. So here you just remember one thing: a plane x equal to 3, right? A plane x equal to 3 in a sense, we know that plane is perpendicular to x-axis. So plane is perpendicular to x-axis in the sense what? Electric field is in x direction, right? Electric field is in x direction, right? So therefore, there is no electric field in y and z directions, right? There is no electric field in y and z direction. So therefore, y coordinate and z coordinate, no need to consider. You can neglect, right? Y coordinate and z coordinate you can neglect. So therefore, x equal to 1. So x equal to 1 is where? Somewhere here, right? So this is x equal to 1, right? So therefore, this is the point, right? So x equal to 3 plane, and we need to determine electric field at a point B, right, at a point P x equal to 1, right? So therefore, electric field E bar is equal to rho s by 2 epsilon naught A n bar. So this is the formula we know. Rho s is given, right? Rho s is equal to 10 nanocoulomb per meter square, and epsilon naught is a constant whose value is known, 10 power minus 9 by 36 pi, right? And we have to determine a n bar, right? We have to determine a n bar, the direction of electric field. So now from this figure, what is the direction of electric field? From the discussion which I have made just now, right? Electric field always directs towards the point. Here is the point, and the direction of electric field will be like this. So this is the point P, and the direction of electric field, right? The direction of electric field is towards the point. So this is the direction of electric field, right? So because the electric field point directs towards the point, right? Towards the point. So therefore, in this direction. So in this direction, in the sense what? Towards negative x-axis, right? Towards negative x-axis. So therefore, a n bar is equal to what? A n bar. A n bar is equal to minus ax bar, right? Minus ax bar, right? So therefore, E bar is equal to 10 nano 10 into 10 power minus 9 divided by 2 into 2 into epsilon naught. Epsilon naught is 10 power minus 9 by 36 pi, right? And a n bar is minus ax bar, right? Minus ax bar, and whose value is minus 180 pi ax bar. So this is the answer, right? So therefore, from this we can say that the electric field is in x direction. Minus, here we have minus ax bar, right? So electric field is in electric field is in negative x direction. Next step. So this is how we can do the problem. Very simple, right? And we will take a few more problems so that you will understand even more clearly about surface charge, right? So on the other hand, if the field contains, right, earlier we have discussed, if the field contains one point charge and one line charge, what is electric field? Electric field is the vector sum of field due to point charge and field due to line charge, right? If the system contains one point charge, one line charge, and one surface charge, what is the total electric field? The total electric field is the vector sum of electric field due to point charge, electric field due to line charge, and electric field due to surface charge. So this is how we can do this, right? So with this, let us close the session, and we will continue in the next class. Right? So thank you very much for your patient listening. I request you to attend regularly. If you have any doubts, you can chat me. You can raise your questions and you can put your doubt on the chat box.